Hello everybody, Adam Lusek here, and today we're going to be setting up Truly Multimodal RAG, a vector database that can store images, audio, video, and text all at once that will allow us to search through all four modalities with just a text query and run vector similarity search between text and audio, text and video, text and images, and text. So ever since my last video, where we checked out ChromaDB's multimodal integration with OpenClip embedding functions, allowing us to use the OpenClip model to embed both images and text the same way, which allows us to generate embeddings for images, store them in a vector database, and then run similarity searches from the same embedding function over text, allowing us to do direct text to image querying without the use of any metadata or alt text querying that would rely on actual text to text retrieval. I've been interested in how to actually apply this idea to the other two modalities that are lacking, video and audio. And so when I came across this, the contrastive language audio pre-training model, I knew I had to put it to the test because this would allow us to do what the clip model was able to do with images for audio. So just to give a quick refresher on what the clip model is before we show how it's applied to audio, the clip model originally came out of OpenAI's research, and it's essentially their pre-training of an image encoder and a text encoder to predict which images were paired with which text in their dataset of 32,768 randomly sampled text-image pairs. What this essentially allows it to do then is do direct zero-shot classification of images, where it can look at an image embedding and a text embedding and compare how similar the two are without ever having seen the text and without ever having seen the image before in its dataset. In our prior example, when we were looking at clip embeddings, we applied this to a bunch of fashion photos where we embedded 1,000 fashion photos and then we're able to do plain text queries using the clip embeddings over those photos to directly retrieve the photos. So we can see here that our query of black skirt returned 5 photos of models in black skirts. And this is great because it allows us to use the same embedding function, the clip model, to embed all of the images into our vector database, and then also be able to embed the text to run the similarity search using the same embedding function. Hopping back to the clap model, LAION essentially took all of the same ideas of the clip model and images, but now applying them to audio. So using their contrastive language audio pre-training on an embedding model, we're now able to do exactly what Clip was able to do with images using clap and audio. And so this means using the clap model, we can perform zero-shot audio classification using the same embedding function to generate the embeddings for the audio files, and then also for the text that we'll be searching the audio files over. So let's see how that's all set up. We're going to be using ChromaDB again, since they have this multimodal capability already built in, and then using and taking advantage of some of its open source nature, we're going to be plugging in a few of our own features into ChromaDB to then support the clap model for audio retrieval. The dataset that we'll be embedding and using for this example is going to be the ESC50 dataset, which contains 2,000 different environmental sounds and should be perfect for this demonstration because I really wanted to show how it's able to do the sound classification that doesn't rely solely on the transcription. When doing a little bit of the pre-research for this, I saw that a lot of the embeddings that claim to be able to embed audio really just ran it through something like the Whisper model to retrieve the text, and then embedded the text for text-to-text retrieval that then pathed back to the audio file. This is not what I wanted to do because I wanted to do direct text to audio retrieval similar to what we did in Clip. So using this dataset, this will be a perfect example. We're just going to be loading that through Hugging Face and then saving all of the files locally. And the reason we're saving these files locally is because ChromaDB doesn't actually store all of these files within its vector database. It will just store the embeddings and then the path on your file directory to those files. And so if you look at ChromaDB's multimodal documentation, you can see that what you need to add a collection with multimodal capabilities is a name, an embedding function, and a data loader. The data loader goes back to what I was saying about ChromaDB, not actually storing the file in the database itself, but it'll actually use a data loader to path over to the data and then load it when need be, when it's retrieved or during the embedding process. The embedding function is then, of course, going to be the function that will be able to take both the text and the modality of choice and be able to generate the embeddings from it, which in its built-in functionality is the clip embedding function. So what we need to do is create a custom data loader for audio and a custom embedding function for audio. And so starting with the data loader, what I have here is the custom audio loader built out. Essentially what it'll do is it'll take in an audio file, do a little bit of pre-processing to ensure that everything's in a standardized format, and then return it in a form that the embedding function can actually handle. And so what it'll do is it'll convert it to 48 kilohertz if it's not already, convert it to mono, and then return from the audio file a waveform tensor from PyTorch. The waveform tensor is then going to be passed into our clap embedding function, which we have here, and the clap embedding function takes in a few different things. It can either take in the waveform or it can take in a text document. And this is how we're going to be able to use the same embedding function to embed both the audio and the text that we want to run the similarity search between the text and the audio from. And so we path over to the larger clap general model to load it. And then within this class, there are two encoding functions. We check if it's an audio tensor. If it is, then it'll process that and return the audio embedding. But if it's text, it'll just process the text and return the text embedding. And so using the same embedding function with the larger clap general model, this is how we're going to be able to generate effective embeddings that will allow us to run the similarity search between audio and audio or text and audio in the retrieval step later. And so then setting up our audio collection is as simple as using the get or create collection method from our ChromaDB client, passing in a name, which I've said audio collection, and then we can pass in our embedding function and our data loader, which are our custom clap embedding function and our custom audio loader here. And so then after we've added all of the files to this, we can test it for retrieval. So I have a quick testing function right here that'll do just that. Essentially, all we need to do is path over to our collection and then use the query method, where we can then pass in texts, how many results we want to return, and then including the URIs and the distances. It will always return 5 results, so I wanted the distances so that we can do a little bit of distance-based filtering, and then the URIs are necessary because that will be the paths to the original audio files so that we can actually use them to display. So let's try this out by searching for water droplet with a max distance of 1.5 over our ESC50 audio database. So let's return 5 audio files here, which they don't have great names like 188293, so let's listen to them and see if it sounds like water droplets. Sounds like water droplets, that's great. So using the clap model, we are able to embed all of the audio files into our vector database. And then because we're able to use the same embedding function with the clap model to embed our text and run the similarity search, we can use zero-shot classification capabilities of the model to run and retrieve similar audio files to our text. So let's try this one more time with something different. I'm just going to put in dog here and see what happens. So it's returned 5 here, and let's listen to one. Sounds like a dog barking. That's definitely a dog barking. Great, so now we have audio files able to be indexed into our Chroma database, but what about the other 3 modalities? Images, text, and video. Wouldn't be true multimodal RAG without all 4 of them. So let's tackle images next, because we already know that this is built in, and we've already used it in our other video, which I'll have linked in the description below, to do some image retrieval. So let's get that started. The dataset that I'll be using is this one that I found on Hugging Face that essentially just includes 4,000 stock photos that are all under the Creative Commons 0 license. One of the things that I did found is that there were a couple corrupted files, so I just have this script here to remove them, and then we save them all to our file system locally, similar to what we did with the audio files because we'll be pathing to them through the URIs, and then we can use the open clip embeddings and image loader that come built in with ChromaDB to both embed these and have a viable way of loading the images. If you're interested in what clip model is actually being used under the hood here in ChromaDB, it turns out to be this one. The Clip Vision Transformer Large 14 LION 2B S32B B82K, definitely a mouthful, Clip Vision Transformer L14 model. And so we're going to be using that and just taking in the image loader and the open clip embedding function that comes from their already pre-built integration with the open clip library and creating our collection, the image collection here, passing in the embedding function and passing in the data loader. Very similar to what we did with the audio files, all we're going to be doing is passing in all of the IDs, which is just going to be the names of the images, and then the URIs, which is going to be the paths of the images, into our collection here, and then adding them there. And then so now this will allow us to be able to query this and then use the clip embedding function in the image loader with just general text to actually run direct zero-shot similarity search over all of our images, using pretty much the same retrieval function, but this time just a little bit augmented for our image collection. Let's try it out with water droplets. There we go. Seeing some images of water droplets. And then similar to our second example, let's try dog. So would you look at that? 5 images of dogs. So image search with direct clip embeddings from text to image is working perfectly. So now we have audio and images able to be queried just from text. So now that our first 2 modalities are added to our database, images and audio, let's do the classic text and add some text in there. So the example dataset that I'll be using is a subset of the entire Wikipedia dataset that I found here on Hugging Face. And essentially this is just a bunch of Wikipedia articles and then their corresponding text. So this is going to be perfect as we're generally building a pretty open, non-specialized database right now with just stock photos and stock images. Let's get some general knowledge in there as well. So this has 25,000 articles, and we're going to add all of them to our database. If you're looking at this video about multimodal reg, you likely already know how general text-based retrieval works, but just to give a little bit of context as to what Chrome is using, they're using the Sentence Transformers All-Mini-LM L6v2 embedding model. So to take advantage of actually knowing that, what I'm going to do is do a little bit of pre-processing. Since 25,000 rows of articles is a little bit to process, what I'm going to do is do a bit of batch processing with this quick script here and take advantage of our GPU capabilities on our Google Colab. All this is going to do is load the All-Mini-LM L6v2 embedding model, and then in batches of 128, run through the 25,000 documents and then create the embeddings. This will put it all into a JSON file as well that we can use to then just import back into our vector database, which is exactly what we're going to be doing here. We have a quick helper function that will load all of the necessary information from our JSON file and then split it out into separate variables so that we can put them all into the right spots. And then we create the text collection. And so we don't need to pass in an embedding function or URIs because text is actually stored within the database itself. And then since this is sort of the standard use case for ChromaDB and for vector databases, it doesn't actually need to be specified that we're doing text. Normally the odd things to do are, audio and video and images and whatnot that we were showing before. So it'll automatically use the All-Mini-LM model here and then use all of the regular loading and stuff that it does for text here. But all we need to do is add that in. And then because ChromaDB has a max size that you can actually insert data in of 5,461 entries, which I learned when trying to insert all 25,000 entries in one go. I created another quick function here that will just slice up our data into batches and then insert it in with 5. So now we'll be able to query over our database for text as well as audio and images. And so to test that out, we've got, once again, another helper function to test. And running this on just water, let's see what it comes up with. It's going to load the model real quick. And then here we go. We've got water. We've got H2O, lovely Australian show, things about water pollution, rain, heavy water. That's great. Let's also try it on the second example option of the day, dog. Let's see what it comes back. We've got Doge, meme, pet, Pyrenean mountain dog, Dogecoin, Labrador retriever. So great. This is able to run our similarity search and retrieval for text-based systems here perfectly well. So if you've been keeping up, you'll know now that we have audio in there, we've got text in there, we've got images in there, and so there's finally one last thing that we need to be able to embed and index, and that is videos. And so when doing the research on this, I was trying to find if there was some sort of clip-clap equivalent for videos, and there actually is. LAION themselves has video clip right here. That is a clip-based video embedding model. And then there's also OpenGV Lab that have vClip, which is a simple video clip for transferable video text representation. But the issue that I found is that a lot of these are either difficult to use because there's no direct actual pipeline into vClip on Hugging Face, and then the LAION model is also a little bit outdated from a couple of years ago, so its dependencies are a little bit out of order with some of the other things that we're using in this. So what I did was I looked into the files to see a little bit about how they are doing these embeddings, and what I realized when I looked in there is that these models actually treat videos not as sort of, a video object in and of itself, but as a collection of frames. And frames, what are frames? Essentially just images. And so with that understanding, we can spoof this a little bit ourselves by treating our videos just as a collection of images. And while we might lose a little bit of the robustness of the embedding if we're using an image embedding model like Clip and not a specific video embedding model that takes in the temporal consistency, what my reasoning was is that essentially if we have enough frames of a video, searching over those frames should find the right part of a single video. If something like a dog shows up in a part of a video and there's a frame there, it should find that right part of the video. And then all we need to do is just return back that video, essentially simulating this. And at a bit of a lower, dumbed down level, this is pretty much what's going on behind the scenes of these video clip models, because they're not able to take videos in and of themselves, they just process frames together. So to set that up, what I've done is I've grabbed almost 100 CC0 licensed videos from pexels.com, and I've compressed them into a zip that you can actually download yourself right here from my Google Drive link. And then you can path that into either your collab environment over here or just unzip in your own directory. And then we're going to be converting those videos into collections of frames. And so then all this function is doing is taking the videos, grabbing the first frame, and then in 5-second intervals, grabbing another frame, and then lastly, grabbing the last frame. So every video will at least be the first frame and the last frame if it is under 5 seconds, but if it is over 5 seconds, at each 5-second interval, additional frames will be grabbed. And so this should, with a little bit of loss, be indexed all and point back to the video file when we search over these frames with something like text. And so to index these actually into ChromaDB, we're just going to be making a quick video collection that uses the same clip and image loader, since we're technically using images as frames, but treating them like videos. And then we're just going to be adding all of the frames in there, and then with some additional metadata. And the metadata is going to path back to our video URI, which is the video path, so that when we do retrieve a frame, what we can do is grab what video it's from and then display the video instead of just the frame that's there. So let's give that a shot. And so one of the things to note here is that Collab's really bad at actually displaying videos because their file system is super slow, but we will power through. And I'm going to search for trees. One of the things to note here too is that because we just have 99 videos in here, it's not going to be, the exact best experience of searching for very specific things. And since it's made to return definitely 5 results, you might get some things that aren't necessarily part of your actual text query. But what we can see is that from trees, we were able to get all of these lovely, ooh, that one has some audio, all of these lovely videos that have somewhat a semblance of trees in them. This is phenomenal. Sweet. So if you've been paying attention, we now have all 4 modalities within our single vector database. We have audio, images, video, and text all indexed within separate collections in the same vector database. So what we can do is do full multimodal retrieval now. So I'm going to run this query of San Francisco over our text, audio, image, and video collections and see what it returns. So just from the text, what we can see is that all of these texts about San Francisco, the 49ers, Silicon Valley, San Jose, the Bay Area, we got one audio file. Some of them were filtered out by the max distance. So let's turn that down a little bit. Sounds like a city there. Might not be San Francisco, but I can see how that might be pulled up. And then a bunch of images of what appears to be the Bay Bridge and the Golden Gate Bridge. And then a couple of videos. So these videos, might not be super specifically San Francisco related, but they're getting the city thing here. So we can see that this is all fully multimodal retrieval. We've gotten text, we've gotten audio, we've gotten images, and we've gotten videos, all from just a text query. And we're using direct zero-shot functionality so that we don't need things like descriptors on the audio, images, or videos to be able to retrieve them. But of course, this is multimodal RAG we're talking about, not just multimodal R or just retrieval. So let's actually put in the augmented generation of the retrieval augmented generation part and use our ability to grab both videos, images, audio, and text to do the full suite with a little bit of LLM response on top of it. One of the things to note here is that as of the time of making this, no LLM can actually process audio files as part of its context, but they can do text and images, which is what we'll take advantage of to pass in the text that's retrieved, a frame from the video that's retrieved, and also any of the images that are retrieved. And so to get this RAG step set up, I defined 3 new retrieval functions that instead of retrieving the actual file and displaying them, instead will give me the image path, all of the text as a single list, and then the paths to the frames from the retrieved videos. We'll then be using GPT-4 Omni and a little bit of its vision capabilities to process both the text, a frame of the video, and also the image that's retrieved. For the sake of token consumption and cost, I'm only passing in one frame and one image because it gets a little bit pricey as you pass in more. But essentially, we're going to be using LangChain here, setting up this super simple chain that will allow us to dynamically input the user query, the texts, and then both of the image data here. The system prompt that I'm using is you are a document retrieval assistant that neatly synthesizes and explains the text and images provided by the user from the query. And then we'll be passing in the texts, the image data, and the other image data. To actually run this chain, it'll be expecting an input of a dictionary that has the query, the texts, and then both of the image data encoded in base 64. So I have another function right here that sets up exactly that. It'll take in the user query, grab the frame path, grab the image path, and grab the texts, and then put it all into an inputs dictionary, and then return it all for us to use, which then looks a little bit like this. So let's run it on the query San Francisco. Sweet. So we can see that one image was returned, one video was returned, the audio, which I'm assuming is going to be those city sounds, yep, was returned. And then we have our AI response that took all of the text and synthesized it here. And then we can see that it also looked at the frame. The first image shows a scenic view of San Francisco with the Bay Bridge. And then the second image is a frame from a video depicting a vibrant cityscape at night. So it was able to take in the image, the video as context. We just display the audio that's retrieved because unfortunately it can't be processed by the LLM. And then all of the text that we got from our Wikipedia dataset is neatly synthesized into this response here, making it a full, true, multimodal retrieval augmented generation setup. Great, so with that being said, we've set up full modality retrieval augmented generation using ChromaDB, a couple of our own specific embedding and loading functions, and some fancy tricks to process videos. So hope this was super educational and enjoyable for you all. If you enjoyed it, leave a like. If you have any questions, leave a comment. And if you want to see more like this and support the channel, consider subscribing. Thank you so much. All of the resources will be in the description below, and I hope you have a great day.